Alright, this will be the last of the recordings for this year anyway. Dealing with maclaurin series. This is essentially an algorithm. There's a lot of theory behind this that we don't have time to get into this year, but we should be able to handle the algorithm, and I'll show you how it works. Starting with an example, we can make a maclaurin series expansion for the square root of 1 plus x. This will give you a series approximation or a polynomial approximation of this particular function. Here's how we do. You take the derivative. Now notice the notation. This is f with the little 0 in parentheses of x. That's the 0th derivative, if you will, or the original function. I just wrote it in exponential form. Then the first derivative is with a 1, second with a 2, and third, and so forth. This change in derivative notation is because we're going to be taking multiple derivatives, so by the time we get to the 7th derivative, potentially, you would have 7 prime dashes there, and that's kind of cumbersome, so we change the notation. The trick is to find the derivative. If we need 4 non-zero terms, we need to take the derivative and make sure that when x equals 0, the value of that function is non-zero. So, continuing taking the derivative repeatedly. Fortunately, this is a simple derivative to take, and with 0 to 3, that makes 4 terms, and when x equals 0, each of these variable expressions turns into 1. So the first is, or the initial is 1, 1/2, negative 1/4, positive 3/8, and that trend would continue. So to write the polynomial expansion, we're going to write, and I'll let it write out first. We've got the first at 0, which is 1, to the 1/2 power, so that's this whole part here evaluated at 0, over 0 factorial, and here we're going to evaluate at 0 over 1 factorial times x to the 1, evaluated at 0, the second derivative, over 2 factorial times x to the 2, so you can see how the pattern works. We just take the nth derivative, starting with 0, we take the nth derivative, and then you take x to that power, and we take the n factorial in the denominator. This creates a polynomial that looks much simpler in this form, just a cubic polynomial, and I'll explore how this looks graphically with a different maclaurin series. But that's essentially the algorithm. It's a pattern. Now you can actually see the pattern in generalized form in your formula packet you'll see at the end of this video. So this time we're going to look at the natural log of 1 plus the sine of x. Now this happens to be a composite function, and there will be a more efficient way of doing this, but once again, because of our time crunch, I'll have to show you the sort of slightly more tedious approach. Nonetheless, the first up to the x to the 4th for this particular function, it's composite, is going to end up looking like this. It's a relatively clean polynomial, it turns out, but it involves a little bit of fidgety calculus. We have to remember the chain rule. So the derivative of natural log times the derivative of 1 plus sine of x. And by the way, evaluating at 0 right away, so we have these values. We have 0 for the first term, 1 for the second term coefficient. And second derivative here, we have to use the quotient rule, and once we apply the quotient rule, we have to distribute the sine of x. And here I'm going to make an assumption that we know the negative sine squared minus the cosine squared is going to be negative 1, because we factor out the 1, sine squared cosine squared equals 1, so that's where that 1 came from. Negative sine x carries down, and it turns out we can factor this to sine of x plus 1. We could factor it with 1 of the denominator, and this makes the second derivative much easier to differentiate. For the third derivative, all of this is of course a Calc 1 review, but nonetheless I have f0, f prime of 0, a second derivative at 0, third derivative at 0. I still need the fourth derivative, because this is the x to the 0, x to the 1, x squared, x cubed. We need one more. So this one actually is going to be rather tedious. I'll skip to the end here. If you want to screenshot this or pause now and just take a look at how this is done. But essentially it's using identities and quadratic factoring to get a simplified form, and I evaluate f fourth derivative at 0 to get -2. Compiling all of these derivatives at 0 gives us a format for our pattern. We start with 0, that's the 0 over here, over 0 factorial, 1 over 1 factorial x, -1 over 2 factorial x squared, 1 over 3 factorial x cubed, and -2, that's this -2 here, over 4 factorial x to the fourth, and all of the algebra is nice and simple after this. We get the expression that we were told to show. So if you show all the work from the previous slide, this one and this one, and then put it all together in this form, you'll be in good shape. Now, approximations. When we had a polynomial like this one to the fourth degree, this is going to give us a almost a pretty decent graph of the natural log of 1 plus the sine of x for small values of x. As x gets larger, this polynomial is going to diverge from this particular function. You'll see that graphically again in a few moments. Now, the premise here, though, is that there is a series that goes out to infinity terms, but there is approximation that goes out just out to n. Like in the last case, we went to n equals 4. This polynomial is going to almost be equal to this infinite polynomial over here. So this is what's called p sub n of x, represents this little guy right here. That's all of the up to n. Now, depending on the number n, so this is taking the y equals the sine of x, and this is the maclaurin series for the sine of x, and in this graph we are just going up to the fourth derivative. As you can see, at the fourth derivative, in between these boundaries we get a perfect approximation, and then the polynomial diverges from the sine wave. If we were to go to eighth derivative, you can see we have a much larger portion of the sine wave is now captured by this polynomial. So the further we iterate, the closer we're going to end up to the sine of x. Now we can understand that if we let n approach infinity, this polynomial could potentially become the whole sine wave. Sometimes it does for some functions, like the sine it does, like e to the x it does. There are other functions where the maclaurin polynomial does not infinitely approximate the function, but that's again for another day. So I'm going to demonstrate the second degree approximation for e to the x. This is just really straightforward because the derivative of e to the x is e to the x. So evaluating e to the 0 in every single term in the polynomial, and then we just do ascending powers from 0 for the x powers and coefficients on the bottom, and it makes this simple quadratic polynomial. Now, here's the thing. If we let this series go out to infinity, it's going to be an approximation for e to the x. We only let n go out to 2, and now we have a remaining fraction, a remainder, if you will. And so this is what's going to be used to determine the maximum error. How close is this approximation to the actual value of e at any value for x? In this case, to find the next or the remainder function, we basically just do the very next iteration. Since in this case we went all the way to n equals 2, then we're going to do f of the third derivative evaluated at c, this is an important point, over n factorial, and this is actually supposed to be n plus 1 factorial. Let me change that. That didn't work well. N plus 1 factorial. Get that right. Anyway, this is then the next term in the Taylor polynomial. The catch here is we're going to evaluate it at, we're going to evaluate at c. C is any number less than the x where we're trying to approximate. This will become clearer in a moment. But basically, well, let me just show you. In this specific example, we're going to approximate e to the x by its second degree maclaurin polynomial. That's what we just did. It was on the previous slide. Here's the part now. Give an upper bound to 4 decimal places on the error when using this approximation to find e to the 0.75. So basically what they're saying is e to the 0.75 is a number. We put it in our calculator, we can find out what that number is. However, if we use this polynomial, this polynomial right here, or this term of the polynomial, we can get an approximation that'll be close to the value of e to the 0.75. So, to demonstrate, first of all, we have the second degree maclaurin polynomial approximation. Then we find the next term. That will be the third derivative evaluated at c. Notice again, this is c, not evaluated at 0, but evaluated at some number less than x. In this case now, x is 0.75, so we're going to have a c value that's somewhere between 0 and 0.75. It might be the endpoint, we'll see. Anyway, the third derivative is still e to the x, so we're just going to have e to the c times x cubed over 3 factorial. So this is how we get the error. We're basically going to assume that if c, let me start over. This is the I apologize. Right here is the error function for any value of x. Now we're going to evaluate the error function at 0.75. We put 0.75 to the third over 3 factorial, and then we still have e to the c. So what about that c value? All we're going to do now is kind of like a comparison test. We just need to figure out what's the largest possible value that that this whole remainder could be, given that c could be any number between 0 and 0.75. It turns out that if we use the largest possible value of x, that will be an upper bound for my error. So the largest that my number could be away, remember this is an approximation for e to the x, and if I put in 0.75, this approximation is going to be within 14% points away from the actual value of e to the 0.75. I know that's kind of a lot to take in, but you might want to pause and maybe watch a con video and catch on or something. Anyway, this is a graphical representation. We have the polynomial approximation, which is the red curve, and we have e to the x as the actual values. And the actual difference is 0.0875, which is less than the maximum difference that I calculated with my estimate. Now remember, this predates the calculator, so we wouldn't have known this particular exact difference, but what we had is proof that the second degree approximation is at least this close to the actual value of the function. Now, here's the deal. This error function, which again represents the next term in our polynomial approximation, is special. If we can prove that the limit, as n goes to infinity, of the absolute value of the error function approaches 0, then the infinite maclaurin series is a valid representation of the function for all values of x. So if you remember, I'll even take you back to here. Where is that graph? It shows up really quick. I think that's what it is. Here we go. There. We could see that as the number of terms in the polynomial increases, we get a closer and closer approximation. And I said in some cases, if we allow the iterations to go out to infinity, the polynomial will be an exact replica of the original given function. So it's a polynomial expansion of the function to the letter, to the exact number, all the way up for all values of x. Now, in some Taylor polynomials, there are certain values of x that are unacceptable. They won't give you a total approximation for the function. But if we can take the limit of our error function, and that error becomes 0 eventually, that essentially says there is no more error between your polynomial and the actual original given function. So this is an ideal situation. So the infinite maclaurin series is valid representation of the function for all values of x in the real numbers. Now, for e to the x, we know that every derivative we take of e to the x is e to the x. And so if we take our error function, we're essentially taking the limit as n goes to infinity of e to the c times x to the n plus 1, the next iteration in the series, and over n plus 1 factorial. Now, this limit does approach 0. You can show that in a calculator. You can prove it in a variety of different ways. Because of time, I'm not proving it, but we can infer this to be true. It's one of those convergent sequences, essentially converges to 0. Anyway, the conclusion then is that e to the x can be approximated by this Taylor maclaurin expansion for all values of x. So that makes that a very special maclaurin series. Now, this one I'm going to go through quickly because this is getting kind of a long video, but I'm going to show you the first 4 non-zero, or sorry, the upper bound error doing a maclaurin expansion estimating at x equals 0.5 for the tangent of x. Now what's happening while I'm talking is all of the derivatives are being taken, and this could be a little soul crushing, and so again this would be one of those where you pause the video and study how I take each derivative. Right now I've got all the way up to the third derivative, and I managed to make it just in terms of secant, so that hopefully the next derivative will be a little bit easier. This is the fourth derivative finally, and I'm going to skip to the end here, and I'm sorry, I wrote examine this function and I can't remember why. Oh yeah, so let me bear with me again, I'm sorry. It's been a long day. The fourth term in my iteration, so that's why I had to take the fourth derivative. Let me go back here. I took the fourth derivative. This then is going to be the key to giving me my remainder function, that error function that we've seen. So what we're going to do is examine the fact that over the range of values, oh no, this went way too far. There. This is the fourth derivative. This is my remainder, or going to be part of my remainder function, and I looked at x being 0 all the way up to 0.5. So these are different values that I could choose for c, and it shows that the endpoint is the largest value because this is an increasing function over time. So the x equals 0.5 is what I'm going to use to give me an upper bound. I'm going to use x equals 0.5 to account for my c value. This c value right here, I know that the fourth derivative is largest when I choose x equals 0.5. So this is how I make a comparison. This is the largest possible value, which turns out to be 0.4279 or 0.428 going to 3 sig figs. Again, a lot to take in. You can check out other vids on maclaurin series to clarify this a little bit more. What you'll see probably is more about the Taylor series. And I didn't do any examples of Taylor series, but I want to point out first of all that the Taylor approximations are actually in your formula packet already. And so you can count on this as a format. And notice the maclaurin series is simply evaluating each derivative at 0. All we're doing in a Taylor approximation is shifting our polynomial from 0 to some arbitrary a value. So we're shifting it to the right if a is positive. So instead of evaluating f prime of 0 or f prime of 7 or f prime of whatever, we're going to evaluate f prime of a, f double prime of a. So instead of 0, we evaluate at a. So all it is just a transformation, a shift. Should work out the same, exactly the same algorithm, the same way for finding the error function. So this Lagrange form is the error function. That is the next iteration in the polynomial that we use to approximate how close our approximation is, or use to determine how close our approximation is. Finally, these are also in your formula packet, and you can rely on those as sort of givens. So for example, if you have a sine of x, you can use this as the Taylor approximation and follow the pattern all the way out. Notice it's an alternating series. This will be handy if you have something like a composite function. If we have e to the 2x, all we have to do is use the e to the x expansion, but we just use the composite. We put the 2x inside. So this would be 1 plus 2x squared over 2 factorial and so on. Alright, so thanks for watching. Good luck.